Hello everybody. So let's discuss about the solutions of problems that were part of your daily quiz of second week of April. Okay, so this is regarding the mathematics daily quiz. Okay, so there were around 4 questions, and we'll discuss them one by one. So this week's questions were on linear algebra topic. So all of them are related to the properties of matrices. Related to eigenvalues, eigenvectors, determinants, etc., etc. Okay. So we have covered all of these things in our regular classes. So if you have attended those, it should be easier for you. Okay. So let's start. So this is the first question where you're supposed to find the eigenvalues for the following matrix A, which is a 3 by 3 matrix. Okay. Which is given as follows, and that is the first part of the question. And if eigenvalues are arranged in increasing order, irrespective of their sign, and they need not to be distinct, so it can be a case of repeated eigenvalues. So finally, you are supposed to evaluate this expression. So once you know the eigenvalues, you can evaluate this expression. That's not a big issue. Okay. So so now usually students who know some properties of eigenvalues, etc., they tend to use the property where the summation of eigenvalues is nothing but the trace of this matrix A. Okay. Here the trace comes out to be plus 5, because 7 minus 5 plus 3 is 10 minus 5 is 5. And you can again, another property of eigenvalues is product of all the eigenvalues for a matrix is nothing but its determinant. Okay. But it is not possible to solve this question using this two commonly used properties of eigenvalues. Okay. Why? Because the thing is, you have 3 unknowns, lambda 1, lambda 2, lambda 3, and you have only 2 equations. So this is not a consistent system of linear equations, and you cannot find the solution here. So therefore, this is a question where you are supposed to solve this question by a conventional method. Okay. And what is the conventional method? In conventional method, you are supposed to first write the characteristic polynomial for the given matrix, which is nothing but determinant of A minus lambda I equal to 0, and then calculate the determinant of that matrix, and then solve for the roots of characteristic polynomial, and that will give you eigenvalues. Okay. So let's do that. Okay. So characteristic polynomial for a matrix is given by the standard formula, determinant of A minus lambda I equal to 0. Okay. So A is the given 3 by 3 matrix, lambda represents eigenvalues, and I is the identity matrix of same order as that of A. Okay. So if you do that, what you'll get is 3 by 3 matrix. Only the difference will be of diagonal elements will be subtracted by lambda, each one of them. Okay. So 7 minus 5, 3. So it will be minus 5 minus lambda, and then it will be 3 minus lambda. These two are 0, 0, and the first one was minus 4. Okay. So of principal diagonal elements do not change, they remain as it is. So it was 8, 6, and minus 6. Okay, and this determinant must be 0. So now one way to solve this is, which is the conventional way, you basically evaluate this determinant of this 3 by 3 matrix by the conventional method. But here, since we are solving it, you can do that. I mean, conventional determinant calculation, everybody should be aware of how to do that for a 3 by 3 matrix. But there is one easier way to do it also. Okay, and that is using cofactor expansion. Okay. Cofactor expansion along third column of this matrix. Okay. Why do I choose third column? Because if you pay attention, third column has 2 elements equal to 0, and the last element is 3 minus lambda. So this cofactor expansion to calculate the determinant of a matrix is also an interesting concept, and we have also discussed in our regular classes. So here the advantage is the calculations become easier. Okay. Why? Because this expression will be just equal to the corresponding element multiplied by its cofactor. Okay, and this C13 represents cofactor matrix, or cofactor for, not a matrix, it's just cofactor for first row third element. Okay, then the second row third column element is 0 again. So and then you have 3 minus lambda into C33. Okay, and it has to be equal to 0. So these first two terms anyway are multiplied by 0, so no need to do those calculations. So only this last part you should be considering for further calculations. Okay, so let's solve the rest of the part. So this is 3 minus lambda, and this cofactor for a particular element of a matrix is given by, there is a standard formula. I'll just write it here. Cij is minus 1 power I plus j into mij. Okay, where mij is the minor corresponding to that ijth element. Okay, so C33 is nothing but minus 1 power 6 into M33. Okay, which is just equal to M33. Okay, minor of that third row third column element. Okay, so therefore this expression will become M33 equal to 0. What is minor for that element? You have to eliminate that row and that corresponding column. Okay, and the rest of it, it will be a 2 by 2 matrix, and you have to take the determinant of that. So basically, you will have a 2 by 2 matrix like this: minus 4 minus lambda and minus 4 8. Okay, so you have to evaluate the determinant of this 2 by 2 matrix in order to get its minor. Okay, so you can do that. So this 3 minus lambda term remains as it is. Inside the bracket you have 7 minus lambda minus 5 minus lambda plus 32. Okay, plus 32 because this minus 32 just becomes plus 32. Okay, so that one step I'm just skipping here. Now just expand the bracket and see, the advantage of doing it this way is, see, if you do it conventional way, you will get a cubic polynomial in lambda, and then you are supposed to find the roots of that cubic polynomial. And the standard way to find one root by doing some hit and trial calculations. And once you find one root, then you convert the cubic polynomial into a quadratic polynomial by multiplying that by that factor. Okay, that root factor. So if you use this cofactor method in this problem, you just get a quadratic polynomial inside the square bracket. Okay, and then you can easily solve it, because in the end the objective is to get the roots of this characteristic polynomial in lambda. Okay, so inside the bracket it becomes minus 35 minus 7 lambda plus 5 lambda plus lambda square plus 32 equal to 0. Okay, so then you have lambda square minus 2 lambda minus 2 lambda plus 3. Oh, minus 3 because it is minus 35. So it is minus 3 equal to 0. Okay, so now you can directly write 3 minus lambda, and this is expansion of lambda minus 3 lambda minus 1. Okay. No need to write one square bracket again because it is lambda plus 1, because the product is minus 1 and the sum is minus 2. And now you can clearly see there are 3 roots, right? So the eigenvalues of, the roots are clearly lambda equal to 3, which comes from this first bracket, then lambda equal to 3 again, which comes from this bracket, and finally lambda equal to minus 1, which comes from this last factor. Okay, so these are the unknown eigenvalues of your matrix A. Okay, so this is the first half of the question that you are supposed to find. So the eigenvalues are minus 1, 3, 3. 2 of the eigenvalues are repeated, and that is fine because they have allowed that in the question. Okay, so that is not an issue. But then the thing is, you should pay attention. They are using the lambda 1, lambda 2, lambda 3 notation, and the smallest one is lambda 1 and the largest one is lambda 3. Okay, so if you go by this logic, you'll get lambda 1 as minus 1. Okay, lambda 1 as minus 1. Lambda 2 and lambda 3 are same. Okay, that is allowed, and those are 3. Okay, And finally, you are supposed to evaluate this expression, which is 3 lambda 1 plus 2 lambda 2 plus lambda 3 equal to what? Okay, so that is 3 into minus 1 plus 2 into 3 plus 3. So this minus 3 plus 3 gets cancelled, and 2 into 3 is 6. So 6 is your answer. Okay, and if I'm not wrong, it is yeah, the answer is 6. Okay, so this is the way to solve this question. Unfortunately, you cannot use any tricks to solve it quickly. You have to follow the conventional approach. Okay, and the rest of the part is easier, because basically once you get the eigenvalues, the rest of the things are straightforward. Okay, you just have to arrange them and solve for them. Now let's go to the second question, where you have a matrix A whose eigenvalues are given as minus half, 1 by 4 and 1, and we define new matrix B, which is combination of matrix A inverse and some identity matrix operation. And then PQR are eigenvalues for this matrix B, and again by magnitude the smallest eigenvalue is P and the largest is R. Okay, and here also it is equal to less than or equal to sign, so that means some eigenvalues may be equal. Okay, so that possibility also exists. And now again it is a two-part question. You are supposed to find the value of 2PR by Q. Okay, 2P plus R by Q. And second part is you have to state whether the matrix B is invertible or not. Okay, so for matrix B to be invertible, the determinant of this matrix is non-zero, then we can say the matrix B is invertible, okay, or non-singular. Okay, so this is the classic definition of existence of inverse for a matrix. The condition is the determinant should be non-zero. Okay, so there are 4 options, and you have to choose one of them. Okay, so let's go to the next slide and discuss the solution, because this is an interesting problem, because you don't know the elements of matrix A, or for that matter you don't know anything else about matrix A except its eigenvalues. Okay, and therefore the first thing that you know is eigenvalues. I will use acronym of EV, okay, because every time we write eigenvalues it becomes cumbersome. So eigenvalues acronym as EVs, okay, of matrix A are given as minus half, 1 by 4 and 1. Okay, and if you remember the properties of eigenvalues that we had discussed in the class, I'll just write eigenvalues, okay, because that was the point of introducing the acronym. So EVs of any matrix inverse will be just inverse of the eigenvalues of that matrix, original matrix. Okay, so just take the inverse of each eigenvalue. Inverse of 1 is still 1. So eigenvalues of A inverse are minus 2, 4 and 1. So we use the classic property of eigenvalues, that if lambda is an eigenvalue of matrix A, then 1 by lambda is an eigenvalue of its inverse. Okay, so basically every eigenvalue gets reciprocal in inverse. Okay, so that is the property that we use to find the eigenvalues of A inverse. Why do we do that? Because in the definition of matrix B, A inverse comes into the picture, and then inside this bracket A inverse minus 3i is there. So basically now the next step is to find the eigenvalues of this A inverse minus 3i matrix. Okay, and again there is a property of eigenvalues for a matrix, which states that if you add or subtract any identity matrix scaled by some scalar, the eigenvalues get shifted by the same distance, which is the scalar multiplier of your identity matrix. Okay, so what it means is, okay, I should not write equal here, let's say colon will use. Okay, so from the eigenvalues of A inverse, you are supposed to subtract 3, because from A inverse matrix you are subtracting 3i matrix. Okay, so therefore eigenvalues will be minus 2 minus 3 comma 4 minus 3 comma 1 minus 3. Okay, that is nothing but minus 5 comma 1 comma minus 2. Okay, so these are the eigenvalues of matrix which is given by A inverse minus 3i. Okay, and then next step is to take the transpose in the definition of B. Okay, so basically we are trying to get the matrix B by doing these manipulations and directly get the eigenvalues for matrix B. Okay, so you should know that again the property of eigenvalues is eigenvalues of matrix A and A transpose are same. Okay, so therefore the eigenvalues of this matrix, which is A inverse minus 3i transpose, will be same as that A inverse minus 3i matrix eigenvalues. Okay, so same. So the eigenvalues, even if you take the transpose, are still minus 1, minus 5, 1, minus 2. Okay, and now for the last part of this definition of matrix B, what they are doing is they are adding 5i in order to get the matrix B. So whatever we did in this second case, here we subtracted minus 3 from every eigenvalue. Now in the last step you have to add 5 to every eigenvalue. Okay, so therefore the eigenvalues of this matrix B, which is given as A inverse minus 3i transpose plus 5i, are nothing but minus 5 plus 5, comma 1 plus 5 and minus 2 plus 5. Okay, so basically just add 5 to all the eigenvalues because we are adding 5i to the transpose. Okay, so therefore the eigenvalues of your matrix B are nothing but minus 5 plus 5 is 0, 6 and 3. Okay, so even without knowing the matrix, you could find the eigenvalues because you knew the eigenvalues of the initial matrix A, and then it was just a manipulation between uh, some A inverse, transpose, and all those properties. Okay, so we found the eigenvalues of matrix B. Next is now we have to assign them as PQR. So magnitude wise the P is smallest and R is the largest. Okay, so therefore your P value is 0, Q value is 3, and R is the largest, so R is 6. Okay, and then you are supposed to evaluate the ratio of 2P plus R by Q. Okay, so you can directly do that. So 2 into 0, R is 6 divided by Q, 3. So it is 6 by 3 and 2. Okay, so if you look at your options, two options you can just eliminate because these are options which are not correct, A and D. So now the fight is between B and C. And as I told you, for matrix B to be invertible, its determinant has to be non-zero. Okay, so now you know the eigenvalues of matrix B, and what you can use the property that product of the eigenvalues of matrix B is nothing but the determinant of your matrix B. Okay, maybe we'll go to the next slide. So determinant of matrix B is nothing but product of all of its eigenvalues, and since one of the eigenvalue is 0, the determinant is 0. So that means B inverse does not exist. Okay, or you can call that matrix B is non-invertible. Okay, or you can also call it a singular matrix. There are multiple terminologies for same thing. Okay, so it's a non-invertible matrix because of the determinant equal to 0. So that means the correct answer should be B. Okay, yeah, and the correct answer is B. Okay, so this is the problem where you are supposed to use the properties of eigenvalues of A inverse, A transpose, then plus minus, Ki, all those things, and then you can get the answer. And then depending on the eigenvalues, you are supposed to find some things. Okay, so it was an interesting question. Now let's move on to the next problem, where you have the third question is, they have given you a matrix M which satisfies this M square equal to M condition. And if you had attended my classes, regular classes, this is the characteristic, one of the characteristic of projection matrix also. Okay, so in some previous year question paper, this such question was there. Okay, anyway, so here they are not discussing that, but now we are supposed to find the correct options, and more than one can be correct, so it's a multiple options correct question. Okay, so very important. Sometimes in this question it is explicitly mentioned that more than one are correct, but sometimes it is subtle. You'll not know if you don't read the question properly. So now the first three options are talking about possible eigenvalues of matrix M, and the fourth one is talking about whether the matrix M is invertible or not. So we have to use the same thing which we did in the previous problem. We are supposed to find the determinant of matrix M based on this given condition, and then if the determinant is 0, it's not invertible. If it is non-zero, it is invertible. Okay. So now, the only thing that you have given information that you have is M square equal to M. Okay, you don't know anything else about M, and any other thing is not there. Okay, so here you are supposed to use the inverse of Cayley-Hamilton theorem. Okay, so Cayley-Hamilton theorem says that any square matrix satisfies its own characteristic polynomial or characteristic equation. Okay, but in this question you are supposed to go backwards. Okay, so basically, let's say lambda is an eigenvalue of matrix M. Okay, then this, as per inverse of this Cayley-Hamilton theorem, basically, the Cayley-Hamilton theorem basically says if you have any expression of matrix A, I mean the characteristic polynomial, just replace lambda by that matrix. Okay, but here we are going to replace M by lambda, so that's why it's an inverse thing. Okay, and therefore what you get is, wherever you have M in this equation, first equation, M square equal to M, replace it by lambda. So basically you get lambda square equal to lambda. Therefore lambda square minus lambda is 0. So that means lambda into lambda minus 1 is 0. So that means lambda is 0 or lambda is 1. Okay. So these are two possible eigenvalues for the given matrix M. Now depending on the order of matrix M, these values could be repeated, and different combinations could be there. But these two only possible options are there for eigenvalue. Okay. So minus 1 is not correct, 0 is okay, and 1 is okay. And now the last part, again, as I told you, you are supposed to find the determinant of this matrix. And you can just say, because one of the eigenvalues is 0, so therefore since one of the eigenvalues of matrix M is 0, the determinant of this matrix has to be equal to 0, because the determinant is product of all eigenvalues. Okay, and that means this matrix M is non-invertible. Okay, or you can say M inverse does not exist, or matrix M is singular. Okay, so anything you can say. But since they were asking whether matrix M is invertible or not, it is not. Okay, so last option is also incorrect. So B and C are the correct options. Yeah, okay, B and C are the correct options. Okay, so interesting question. Here it was asked in this M square equal to M, but many times they will give you some polynomial in matrix, that is also called as matrix polynomial or matrix function, and then you are supposed to replace that matrix variable by lambda and get the lambda values. Okay, and inverse is also possible. If you get the characteristic equation, you can replace lambda by the given matrix, and that is also true. Okay, so anything can be asked. Now let's move on to the last question, where yeah. So this is the question where they have given you a 3x3 matrix whose determinant is 2, and then you have to select the correct options. Okay, and again, more than one correct possibility is there. And since all of the options involve calculation of determinant, you are supposed to remember the properties of determinant of a matrix. Okay, we have discussed that extensively in our regular classes. Now, the first property, because if you look at options A and B, they look more or less similar. Just in first option it is multiplied by 2a, in second option it is multiplied by 3. Okay, so the important property of this matrix determinants that you are supposed to take help of is nothing but determinant of Ka, where K is a scalar and A is the matrix, is nothing but equal to K power n into determinant of matrix A. Okay, where this n is nothing but, it is the order of your matrix A. Okay, A will be basically n by n square matrix. Okay. See, there is one other way also to solve this problem. Somebody, if you don't know this or don't remember these properties for your exam, somebody can do, define this matrix, 3 by 3 matrix, such as something like 2, 1, 1. Okay. And rest of the off principal diagonal element 0. So this will ensure that the determinant remains 2, and then you can, verify options A and B. But the problem comes in options D and C and D. Okay, because calculation of A square and A inverse is difficult. Okay, so therefore, like if you're in a, see, if it is only one option correct, you can just verify A and B, but this is more than one. So you are supposed to be careful, and that's why these properties, etc., are important. Okay, so I hope you understand, because calculation of A square and calculation of A inverse will be even more difficult, because it's not easy for a 3 by 3 matrix. Okay, so that's why these properties come in handy. So the first property that we'll use is determinant of K is equal to K power n into determinant of A. Okay, so if you do that, this determinant of 2A, which is our first option, should be 2 power 3 into determinant of A. Okay, the power 3 comes because A is a 3 by 3 matrix. Okay, it is given in the question, it is a 3 by 3 matrix. So therefore, it should be 8 into determinant of A, which is given as 2. So determinant of 2A should be 16. Okay, and it is given as 4. So the first option is incorrect. Let's verify the second option. Determinant of 3A, let's say. It should be 3 cube into determinant of A. Okay, so that is nothing but 3 cube into 2, because determinant of A is 2. So it is 27 into 2, so that is 54. Okay, and yes, they have given it as 54. So A is not correct, B is correct. Now coming to the C and D options. See, for C options, you don't need to calculate A square. There is one very important property of determinant of matrices is nothing but, determinant of. So this is the property that you are supposed to take help of for option C. Okay. So determinant of AB is determinant of A multiplied by determinant of B. Okay. So here, since we are interested in A square, what we can do is replace B by A in this property. Okay. Then what happens? You get determinant of A into A, which is nothing but just A square, and which is our interest of verification here, will be determinant of A into determinant of A. Okay. And it is given as 2. So it will be 2 into 2. So determinant of A square should be 4. Yeah, so it is correct. And last but not least, they are talking about the determinant of A inverse. Okay, so there also there is a standard property of determinant of a matrix, which tells you that determinant of A inverse is just reciprocal of determinant of original matrix A. Okay, that should be 1 by 2, because determinant of A is 2. So determinant of A inverse must be half or 1 by 2. But what is the given option? It is -2, so it is not correct. Okay, so the correct answers are B and C. Okay. Yeah, B and C. Okay, so these are some of the questions where you are supposed to use various properties of determinant of a matrix. Okay, so with that we'll stop and see you next time. Okay, bye.